Welcome to the video lesson for section 2.6, graphs of rational functions. We're going to talk about some different properties of rational functions and some features we need to be able to identify in order to graph. To begin with, let's talk about some vertical asymptotes. So for our definition here, for a vertical asymptote, if you can plug in any x value, which we're going to identify as a, and you get a 0 in the denominator, then the function is going to have a vertical asymptote at the equation x is equal to a. So what we're basically trying to find here are any numbers that you can plug into your denominator to make that value equal to 0. And it's pretty straightforward. So what we're going to do here is we're going to go ahead and we're going to look at our denominators. And I'm going to set just that expression equal to 0. And then we're going to go through the process of solving for x. So I'm going to add 6 on both sides, and then divide by 2, and I get x is equal to 3. So this is now going to be the equation of my vertical asymptote, which basically means that the function is undefined because we know that we can't have a 0 in our denominator. Let's go ahead and look at the example below. We have 1 over 3x minus 6. Same thing, we're going to look at just our denominator. I'm going to take that value, I'm going to set it equal to 0, and I'm going to solve for x. And by doing that, our final answer will be the equation of our vertical asymptote. We're going to add 6 on both sides, and then divide by 3, and I get x is equal to 2. So I identified that my equation for my vertical asymptote for that first example was x equals 3, and that for this one's going to be x is equal to 2. Let's take a look at this 1 over x squared minus 4. Same process. Again, we care about the values that we plug into our denominator to make it equal to 0. So I'm going to take this expression. We have x squared minus 4 is equal to 0, and we're going to solve for x. We're going to add 4 to both sides, and then at this point, we're going to go ahead and take the square root. And don't forget, when we take the square root, you have to add in plus or minus. So we're going to get x is equal to plus or minus 2, which means that we actually have two vertical asymptotes. All right, what I'd like for you to do is go ahead and try to identify the vertical asymptotes for the next example, 1 over x squared minus 9. Go ahead and answer that question, and then check back in to see how you did. All right, so just like we did for the other examples, we're going to go ahead and take our denominator, set it equal to 0. We're going to add 9 to both sides, and then we got to take a square root, and we got to remember when we take the square root that we add in a plus or minus, and we're going to get x is equal to plus or minus 3, and those would be the two equations for our vertical asymptotes. Again, we have x equals positive 3, and x is equal to negative 3. Most of our rational functions are also going to have a horizontal asymptote, so we're going to go ahead and look at that, but the notation got a little messed up here, so I'm going to cover this up, and we're going to write it out. Okay, so our function is going to be f of x is equal to a times x to the nth over b times x to the m power. And there are other terms, but we are looking at the leading coefficient and the degree for both the numerator and the denominator. So if our degrees are the same, if n is equal to m, then we're going to have an asymptote, a horizontal asymptote at the equation y is equal to a over b. So it's going to be a ratio of the coefficients for our biggest terms. If instead n is less than m, which means the bigger degree is in your denominator, then we're automatically going to have the line y is equal to 0 as our horizontal asymptote. And if instead n is actually bigger than m, so then the degree in our numerator is bigger than the degree in our denominator, then we don't have, I'm going to say has no horizontal asymptote. We instead have a slant asymptote, which we will talk about in 2.7. Okay, let's go ahead and talk about this and look at some examples to apply our scenario. So we have scenario 1, where the degrees are the same. We have scenario 2, where the denominator has a larger degree. And we have scenario 3, where the numerator has a larger degree. Okay, let's go ahead and try and take a look at this. Okay, I'm going to look at the biggest term in both my numerator and my denominator. So in my numerator, the biggest term is going to be this 2x, and then my denominator is going to be just an x. I'm going to rewrite this as 2x over x. And I look at my expression, and we're basically just simplifying this. And I notice that the x's will cancel out because they have the same degree. So this is going to be scenario 1, because the degree of my numerator is going to be 1. The degree of my denominator is going to be 1. So this whole thing is going to simplify to be just 2 over 1, which is just 2. So my equation of y is equal to 2 is going to be my horizontal asymptote. If you look at the next example, again, we're trying to identify the biggest term. My numerator only has 1. My denominator has 2, but 3x is bigger because it has an x. So I'm going to go ahead and rewrite this as 2x over 3x because, again, we're picking out those biggest terms. And if I were to simplify this, I see once again this is scenario 1 because my degrees are the same. The x's are going to cancel out and we get just a ratio of our coefficients. And so I'm going to have a horizontal asymptote at the equation y is equal to 2 over 3. Now, if you look at our next example up here at the top, we see that for our numerator, we have 2x cubed. For our denominator, we have 3x. I'm going to go ahead and rewrite this as 2x cubed over 3x. And I see right away that my numerator has a bigger degree. So this is going to be scenario 3. Because the numerator has a bigger degree, we have no horizontal asymptote. If you look at our next example, again, our only term in the numerator is 2x. Our term in our denominator is 3x cubed. That is the biggest value. We're going to go ahead and rewrite this as 2x over 3x cubed. And I see that the degree in my denominator is bigger. It is 3, whereas the degree in my numerator is only 1. And so by default, we automatically have a horizontal asymptote of y is equal to 0. So this would be scenario 2 because our denominator had a bigger degree. All right, the last concept we're going to discuss in section 2.6 is the idea of a hole. So a function has a hole at x is equal to a if the numerator and the denominator have a factor of x minus a. And what we see here with this factor form for our function is that the x minus a's are actually going to cancel out. And because they cancel out, we have this gap in our function. And if we were to look at this on something like Desmos, we would see that there's an actual hole, there's a space in our graph. So we're going to go ahead and identify a couple holes and then also talk about some asymptotes here. Okay, so for example, we want to find the hole. In order to find the holes, we're going to have to factor our functions. I look at that numerator and I notice that it is the difference of squares, so I can automatically factor. Now we have x minus 4, and then we have x plus 4. And then when I look at my denominator, using our favorite quadratic factoring technique, I'm going to go ahead and factor this, and I'm going to get x minus 4, and I get x plus 3. And I see that I have a common factor in my numerator and my denominator, so those can cancel out. And because those cancel out, I'm going to use that factor to identify where my hole is. I take that expression of x minus 4 is equal to 0, and when we solve it, we get x is equal to 4. So I know that I'm going to have a hole when my x value equals 4, but we also need to identify the y value. In order to identify the y value, what we're going to do is we're going to take that value and we're going to plug it into the remaining expression after we simplified. If we plug it into the original expression, then we're going to get 0 over 0 because of this idea of the hole. So I'm going to plug the 4 in, and if I plug it in, then I'm going to get f of 4, which would be 4 plus 4 over 4 plus 3, giving me a value of 8 over 7, which means that my hole is going to be at the point 4 and 8 over 7. And when we get to sketching these things, what we will actually do is draw an open circle to represent that this hole exists within a rational function. All right, moving on to another example. We have 2x squared plus 3x minus 2 over x squared plus x minus 2. Again, we're going to go ahead and try to factor this. You guys can use the butterfly method, the x method, possibly factoring by grouping. Either way, we're going to go ahead and get the following factored form. You have 2x minus 1, and then we have x plus 2. If I look at my denominator and I factor that, I'm going to get x minus 1 and x plus 2. And again, I notice that my common factors of x plus 2 are going to cancel out, which tells me that I'm going to have a hole using that factor at x is equal to negative 2. Again, we're going to take our value of negative 2. We're going to plug it into, not that part. We're going to plug it into the remaining function to figure out the corresponding y value, which means we're evaluating f of negative 2. That's going to be 2 times negative 2 minus 1 over negative 2 minus 1. And that whole thing is going to simplify to be negative 5 over negative 3, which should end up being positive 5 over 3. which means that we have a hole at the following point of -2 and +5/3. All right, we're going to go ahead and try and put some concepts together here. I'm going to go ahead and let you guys know that for these following examples, there are no holes. And one thing that helps me identify that there are, in fact, no holes is if I look at all of my numerators, I have a single term. I have a 4x, a 4x squared, a 3x squared, and a 2x. And I'm not going to get a common factor in both my numerator and my denominator to cancel out. So I know there's not going to be any holes. We're going to go ahead and try and identify the asymptotes, though, and identify our scenarios. For our vertical asymptotes, again, all we're going to do is take our denominators and set it equal to 0. So I'm going to take this 2x plus 8 and set it equal to 0. And we're going to go ahead and solve for x. We're going to subtract 8 on both sides and then divide by 2. And I get x is equal to -4. And again, that is the equation of my vertical asymptote. For my horizontal asymptote, I'm looking at the largest terms of both my numerators and my denominators. So we're going to get 4x over 2x. And if we simplify, this again would be scenario 1. Because I have the same degree in my numerator and my denominator, I'm going to get just 4 over 2, which simplifies to be 2. And that would then be my horizontal asymptote. All right, we're going to go ahead and look at this, another example, 4x squared over x squared minus 9. And what I want you to do is go ahead and identify the vertical asymptotes, and then also identify the horizontal asymptotes, and check your answer and see how you did. So go ahead and do that now, and submit your answer, and then check back in and see what the correct answers are. All right, so we can see that for our vertical asymptotes, again, I took my denominator, I set equal to 0, added 9 and took the square root, and don't forget you add in plus or minus when you take the square root. And then for my horizontal asymptote, I have 4x squared over x squared, which is automatically scenario 1, where the degrees are the same. We see the x squareds cancel, and we just get 4 is equal to y. All right, moving on to our next example, 3x over 2x cubed plus 16. Again, I'm going to challenge you just a little bit. I just want you to identify the horizontal asymptote. So is this scenario 1, scenario 2, or scenario 3? And then what is the actual horizontal asymptote? Go ahead and identify your answer and then check back in and see how you did. All right, for our horizontal asymptote, I look at my biggest terms. We have 3x and 2x cubed. Because my degree and my denominator is automatically bigger, by default, we have y is equal to 0 as our horizontal asymptote. For our vertical asymptotes, we're going to look at just our denominator. And again, I'm going to set that equal to 0. We get 2x cubed plus 16 is equal to 0. I'm going to subtract 16 on both sides and then divide by 2. And now I have to take the cube root, and conveniently, when we take the cube root, we don't have to worry about this plus or minus aspect. I'm going to take the cube root of both sides, and the cube root of -8 is actually going to be -2, and that's going to be our vertical asymptote. All right, we have one last example here. If we look at our denominator, I set that equal to 0. We're going to go ahead and subtract 4 on both sides, and we get our vertical asymptote is going to be x is equal to -4. And then for our horizontal asymptotes, I notice I have 3x squared over x. Because the degree in my numerator is bigger than the degree in my denominator, we automatically are in scenario 3 here, and we have no horizontal asymptote. Again, we'll have that slant asymptote that we'll talk about in 2.7. All right, that does it for the notes. Go ahead and get started on the homework, and good luck.